Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the length of line segment DE that is equal to x, and in the second question, we'll find out the shaded area or the value of the shaded area that is inside this quarter circle. So we'll start with the first question. In the drawing, we have triangle ABC. We know that angle ABC equals to 30 units in its size. Angle ACB, this angle equals to 30 degrees. Also in its length, in its size. And we also know that angle DAE, this angle equals to 60 degrees. And line segment BD equals to 5 units, while line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to x. Okay, so we will focus on triangle ABC. In triangle ABC, you know that those two angles that are equal to each other. Each angle is equal to 30 degrees. So I'll write it down. In triangle ABC, we have two angles that are equal to each other. Angle ABC, this angle, equals to this angle that is actually angle ACB. And both angles are equal to 30 degrees, therefore they are equal to each other. I repeat again, in triangle ABC, angle ABC equals to angle ACB equals to 30 degrees. And according to the rule that in front of equal angles in the triangle there are equal sides, so here in front of this angle we have side, if we focus on triangle ABC, in front of this angle that is equal to 30 degrees, we have side AB. In front of this angle that is also equal to 30 degrees, we have side AC, and according to the rule that I mentioned, side AB must be equal to side AC. Okay, and the fact that those two angles are equal to each other, we derive that side AB equals to side AC. Okay. Here, side AB equals to side AC. Okay, so we will continue to focus on triangle ABC. We know that in any triangle, the sum of the angles are equal to 180 degrees, and especially in triangle ABC, the sum of its angles is equal to 180 degrees. So here we will define angle EAC, we define angle BAD as alpha, we will define angle EAC, this angle is beta, and we know that the sum of the angles in triangle ABC are equal to 180 degrees. The sum of the angles is equal to 180 degrees, so which angles we have in triangle ABC? So this angle equals to 30 degrees, plus this angle that is also equals to 30 degrees, plus this angle that is equal to alpha, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those angles must be equal to 180 degrees. Okay. So here, 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So here we have in this side of the equation 120 degrees plus alpha plus beta is equal to 180 degrees. So here we will subtract 120 degrees from this equation and we will get that here alpha plus beta equals to 180 degrees plus 120 degrees is 60 degrees. So we found out that alpha plus beta equals to 60 degrees. In the next step, we'll do two constructions. Here, from point A, we draw a straight line in such a way that side CA and the straight line together will create angle of alpha. Okay? Side CA and the straight line that we will draw will create angle alpha. So actually here, side CA and the straight line together will create angle alpha. So this angle equals to alpha according to our construction. The second construction that we will do is from point C, we'll draw a straight line in such a way that side AC will create angle of 30 degrees with the straight line. So here, side AC create angle of 30 degrees with a straight line. Then in the next step we will extend the two straight line by straight line until they intersect with each other. And we define the intersection point of the two straight lines as point F. Okay, in this way, by this construction, we created triangle AFC. So I repeat again that angle alpha and this angle that is equal to 30 degrees were created by our construction. Okay, so in the next step, we'll prove that those two triangles can go into each other. So we will actually prove that triangle ABD, this triangle, is congruent to this triangle that is actually triangle AFC that we created by the constructions. So, why those two triangles can go into each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So here, angle BAD, this angle equals to alpha according to our definition. It is equal to this angle that is equal to alpha according to our construction. So it is equal to angle CAF that is equal to alpha. I'll repeat again. Angle BAD equals to angle CAF, and both angles are equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. Side AB equals to side AC. Side AB equals to side AC because of the fact that those two sides are located in front of equal angles. Okay, and finally those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So this angle, that is actually angle ABD, is equal to this angle, that is actually angle ACF. They are both equal to 30 degrees, therefore they are equal to each other. I repeat again, angle ABD equals to angle ACF. They are both equal to 30 degrees, therefore they are equal to each other. Okay, so we actually proved that triangle ABD congruent, this is the sign of congruent, to triangle AFC, according to angle side angle rule. I'll explain what I mean. We actually proved that those two triangles can go into each other according to angle side angle rule. Here, those two angles that are equal to alpha and 30 degrees plus the side that attached to them, that is side AB, are correspondingly congruent to those two angles that are alpha and 30 degrees, and the side that attached to them, that is side AC. So we actually proved that those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we'll conclude two things. The first thing that we will conclude is that side BD equals to side FC. BD equals to FC. And read again. We conclude that BD equals to FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us the question, BD equals to 5 units. So we can write here that BD equals to 5 units, and from this equation 5 equals to BD equals to FC, we will derive that FC is also equal to 5 units. Okay, FC equals to 5 units. So here we can write that FC equals to 5 units. In addition, the second thing that we'll conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. AD equals to AF. Here, AD equals to AF according to the same rule that corresponding sides in congruent triangles are equal to each other. Okay, and if we define side AD as A, here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we derive that AF is also equals to A. AF equals to A. So here we can write down that AF equals to A. In the next step, we'll join points E and F together by a straight line. And we will prove, before that, according to what we have already found out. We have already found out that alpha plus beta equals to 60 degrees. So here angle EAF equals to alpha plus beta, that is to say, it is equal to 30 degrees, to 60 degrees. Okay, according to the equation that alpha plus beta equals to 60 degrees, then angle EAF that is equal to alpha plus beta will be equal to 60 degrees. So in the next step, we'll prove that the green triangle AED, the green triangle ADE, this green triangle is congruent to the orange triangle AEF. Okay, we prove that the green triangle is congruent to the orange triangle. I write it down. We will prove that triangle ADE, that is the green triangle, is congruent to the orange triangle AEF. So why those two triangles can go into each other? First of all, we just right now found out that AD equals to AF equals to A. Those two sides are equal to each other. AD equals to AE equals to A. Repeat again. AD equals to AE equals to A. In addition, those two angles, they are both equals to 60 degrees, therefore they are equal to each other. So here, angle DAE, this angle, is equal to this angle, that is actually angle EAF. And both angles, they are equal to 60 degrees, therefore they are equal to each other. I repeat again. Angle DAE equals to angle EAF. They are both equal to 60 degrees, therefore they are equal to each other. And finally, this side AE, is a common side. So, therefore, this side equals to itself. It's a common side. It belongs to both triangles. So, A equals to AE is a common side. I'll repeat again, side AE equals to side AE is a common side. So we actually proved that the green triangle ADE, is congruent to the orange triangle AEF. According to side angle side rule. Side angle side rule. Okay. Triangle ADE, the green triangle, is congruent to the orange triangle AEF. Triangle AEF, according to side angle side rule. So we'll explain what I mean here. Actually, those two sides and the angle between them in the green triangle congruent to those two sides and the angle between them in the orange triangle. So those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE equals to side AF. DE equals to AF. I'll repeat again. From the fact that the green triangles can go into the orange triangle, we conclude that DE equals to AF according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding sides, that is to say DE and AF, will be equal to each other. So if we define side AF as A, here DE is equal to EF. Repeat again. Side DE is equal to side EF. Here, side DE is equal to side EF. Side DE is equal to side EF. But according to what is given as the question, side DE equals to X. So here we can write down that side DE equals to X, and from this equation X equals to DE equals to EF, we derive that EF is also equals to X. X is the line segment that we are looking for. So here side EF is also equals to X. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. Okay, so what is the law of cosines? Actually, the law of cosines is true in any triangle. So if we have triangle ABC, that could be any triangle. This is triangle ABC. And we know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length. Then the following equation is true. C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So in triangle ABC, that could be any triangle. The following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. As I've already mentioned, we'll implement the law of cosines in this triangle, triangle EFC. So I'll copy triangle EFC here, and we'll implement the law of cosines in this triangle, triangle EFC. Angle FCE, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. Side FC equals to 5 units, side EC equals to 4 units, and side EF equals to X, that is the line segment that we are looking for. So this is triangle EFC that I copied from the original drawing. So we will implement the law of cosines. In this triangle, triangle EFC. according to the law of cosines. If we implement the law of cosines in triangle EFC, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Okay, this equation is the implementation of the law of cosines in this triangle EFC. X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So actually we have here x squared that is equal to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, cosine 60 degrees. Cosine 60 degrees is 1/2, so we substitute cosine 60 degrees by 1/2. So in conclusion, we found out that x squared equals to 16 plus 25 is 41, minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20 is 20, so x squared equals to 20. Here we take a root out of this equation and we get that x equals to, here 41 minus 20 is 21, of course. So we found out that x squared equals to 21. We take a root out of this equation and we get that x equals to the positive root of the square root of 21. The positive root of the positive square root of 21 on terms of numbers, it is equal to 4.58 square units. Okay, so we actually found out that line segment DE that is equal to x, it is actually equals to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 square units. Okay, so we finished with the first question. In the next step, I will present to you the second question. In the drawing, we have a quarter circle. Inside the quarter circle, we have a circle and a semicircle that are tangent to each other at this point. This is the point of tendency between this semicircle and the circle, this circle. And also, this circle is tangent to the semicircle at this point. And our mission is to find out the value of the shaded area. Okay, so first of all, because of the fact that we have here a quarter circle, in any quarter circle, this point is the center of the quarter circle. So we define the center of the quarter circle as point O. I write down here that O is the center of the quarter circle. Okay, point O is the center of the quarter circle. And this angle must be equal to 90 degrees. So this angle equals to 90 degrees. And also we know that in any quarter circle, here this side will define this point is point A. We know that OA is the radius of the quarter circle. We'll define this point as point B. And OB is also the radius of the quarter circle. We define the point of tendency of tangent OA with this circle as point M. So point M is the point of tangency of tangent OA with this circle. Okay? And we define the center of this circle as point P. So point P is the center of the circle, point M is the point of the circle itself, therefore PM is the radius of this circle that is equal to 2 units. So here we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent AB that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency. Therefore, according to rule number 1, tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay? And according to this rule, because of the fact that the radius PM it is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, then this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So we have here two angles that are equal to 90 degrees. In the next step, from point P, we will draw perpendicular on BO. Again, from point P, we will draw perpendicular on BO. So here, according to our construction, this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to our construction. Okay, we'll define the touching point of the perpendicular from point P and BO as N. So actually we created here quadrilateral NPOM. Inside quadrilateral NPOM we have 1, 2, 3 right angles. So I write it down. Inside quadrilateral NPOM we have 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle that is actually angle NPM, this angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, so here we will subtract 270 degrees from this equation, and we'll get that the missing angle NPM is equal to 360 degrees minus 270 degrees. It is equal to 90 degrees, so it is a right angle. So we actually found out that this angle NPM, is a right angle. So we actually found out that inside quadrilateral NPOM we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. Therefore, we will relate to quadrilateral NPOM as a rectangle because it has 4 right angles. So we relate to quadrilateral NPOM as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. Therefore, in rectangle NPOM, its opposite sides are equal to each other. That is to say, PM equals to NO. PM equals to NO according to the rule that the opposite sides of a rectangle are equal to each other. Okay, PM equals to NO. But we know that PM equals to 2 units. So we can write here that PM equals to 2 units. And from this equation 2 equals to PM equals to NO, we will derive that NO is also equals to 2 units. NO is also equals to 2 units. So we can write here that NO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that side NP must be equal to side OM. NP equals to OM. Side NP equals to side OM according to the same rule that the opposite sides of a rectangle are equal to each other. So if we define side OM as x, here side OM equals to x according to our definition, then from this equation NP equals to OM equals to x, we will derive that NP is also equals to x. NP equals to x. In the next step, we will focus at this point, that is the point of tendency between the circle and the quarter circle. That is to say, the circle is tangent to the quarter circle at this point. This is the touching point between the circle and the quarter circle. So here we define the point of tendency with the circle and the quarter circle as point K. So actually we have here an internal lunge between the circle and the quarter circle. That is to say, the circle and the quarter circle are touching each other internally at point K. And whenever you have an internal lunge between two circular shapes, then the straight line that connects their centers together must pass through point K. That is the point of tendency or the touching point between the two circular shapes. The center of point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that connects the two centers together is OP, straight line OP. And according to the rule that I mentioned, the straight line OP must pass through point K. That is the point of tendency of the circle and the quarter circle. So if the straight line OP must pass through point K, it means that OPK is one straight line. So line segment OPK is one straight line. Okay, line segment OPK is one straight line, or in other words, we can say also that points O, P and K, they are all located on the same straight line. I'll repeat it again, we can also say, instead of OPK is one straight line, that the 3 points O, P and K are all located on the same straight line. Okay, so if OPK is one straight line, it means that OK is also a straight line. Okay. OK, line segment OK is a straight line. And it is very important that it passes through point P, because then we can do here, we can find out the values of OP and PK. Okay, and also the value of line segment OK. So point O is the center of the quarter circle. Point K is the point of the quarter circle itself. That is to say, line segment OK is the radius of the quarter circle, because it starts from the center of the quarter circle and ends at point K, that is the point of the quarter circle itself. So OK is the radius of the quarter circle. OK is the radius of the quarter circle. So we will define the radius of the quarter circle as capital R. So it is equals to capital R. That is to say, OK equals to capital R, and it is the radius of the quarter circle. Point P is the center of the circle. Point K is the point of the circle itself. This is exactly the definition of a radius. That is to say, PK is the radius of this circle, that is equal to 2 units according to what is given as the question. So we can write down here that PK equals to 2 units. And what is the value of line segment OP? The value of line segment OP, it is very easy to see from the drawing that OP equals to OK minus PK. Again, OK minus PK equals to OP. Very simple. I'll write it down. Line segment OP equals to OK minus PK. I'll repeat again. Line segment OP equals to OK minus PK. So line segment OP equals to OK. OK equals to R, to capital R. It is the radius of the quarter circle, minus PK. PK equals to 2 units. It is the radius of the circle. So in conclusion, we found out that OP equals to capital R minus 2. So we can write down here that OP equals to capital R minus 2. Now we will implement the Pythagoras theorem on the right triangle, triangle OPM. So I'll copy the right triangle in a new page and we'll implement the Pythagoras theorem on this triangle, triangle OPM. Okay. The hypotenuse OP equals to capital R minus 2. PM equals to 2 units. And OM equals to X. So this is the right triangle, triangle OPM that I copied from the original drawing. This angle of course equals to 90 degrees. So here, according to the Pythagoras theorem by PT, that is a abbreviation for Pythagoras theorem, we'll get that in the right triangle, triangle OPM, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be equation number 1. The square of the hypotenuse is OP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PM squared plus OM squared. Okay, so according to the Pythagoras theorem, OP squared equals to PM squared plus OM squared. So here, the hypotenuse OP equals to R minus 2, so capital R minus 2, so therefore OP squared will be equal to capital R minus 2 squared, and it is equal to PM squared. PM equals to 2, so PM squared is 2 squared, that is 4, plus OM squared. OM equals to X, so OM squared equals to X squared. So in conclusion, we found out that according to equation number 1 and according to the Pythagoras theorem, R minus 2 squared equals to 4 plus X squared. Here we'll open the brackets on this side of equation number 1 and we'll get that R minus 2 squared equals to R squared plus 2 squared, that is actually 4, minus 2 times R times 2 is minus 4R. That is equals to 4 plus X squared. Here we have 4 on both sides of the equation, so 4 will get cancelled. So what is left from equation number 1 after we cancelled 4? What is left? It is actually here we have R squared minus 4R, that is equals to X squared. So according to equation number 1, we actually found out that X squared equals to R squared minus 4R. Okay? In the next step, we'll focus on this point, that is the point of tendency or the touching point between the circle and the semicircle. So we will define the point of tendency of the circle and the semicircle as point H. So we have an external lunge between the circle and the semicircle. That is to say, they are touching each other externally at point H. Point H is the touching point or the point of tendency between the circle and the semicircle. And whenever you have an external lunge between two circular shapes, then the straight line that joins their centers together will pass or must pass through the point of tendency between them. Okay? So here we will define the center of the semicircle as point L. So point L is the center of the semicircle. Point P is the center of the circle. And the straight line that joins their centers together is LP. And according to what I've already said, according to the rule that I mentioned, the straight line LP must pass through point H. So actually, you can write down that line segment LHP is one straight line. Okay, line segment LHP is one straight line. And we also can say it in other words that points L, H, and P, they are all located on the same straight line. I'll repeat again. We can say also that points L, H, and P, they are all located on the same straight line. Okay? So if LHP is a straight line, then LP is also a straight line. So, line segment LP is a straight line. Okay, so point L is the center of the semicircle. Point H is the point of the semicircle itself. That is to say, LH is the radius of the semicircle. That is to say, it is equal to 2 units. Likewise, point P is the center of the circle. Point H is the point of the circle itself. That is to say, HP is the radius of the circle that is also equals to 2 units according to what is given as the question. Okay? So actually we found out that the length of the straight line LP, it is equal to LH plus HP. LP equals to LH plus HP. I'll write it down. The length of the straight line LP is equal to LH or LH plus HP. Repeat again. The length of the straight line LP equals to LH plus HP. So LP equals to LH. LH equals to 2 plus HP. HP also equals to 2. So LP equals to 2 plus 2, that is 4. So we found out that LP equals to 4. And what is the length of line segment LN? The length of line segment LN, it is very easy to see from the drawing that LN equals to BO, that is the radius of the quarter circle, minus BL minus NO. Again, BO minus BL minus NO equals to exactly LN. So I write it down, LN, the length of line segment LN equals to BO, that is the radius of the quarter circle, minus BL, that is the radius of the circle, minus NO. I'll repeat again, the length of line segment LN equals to BO, that is the radius of the quarter circle, that is equal to capital R according to our definition, minus BL. BL here. Point L is the center of the semicircle. Point B is the point of the semicircle itself. That is to say, LB is the radius of the semicircle, that is equal to 2 units according to what is given as the question. So here BL equals to 2 minus NO. NO also equals to 2. You can see that NO equals to 2. NO equals to 2 units. Okay? So we substitute NO by 2. So in conclusion, we found out that the length of line segment LN equals to capital R minus 2 is minus 4. So it is equals to capital R minus 4. Here LN equals to line segment LN equals to capital R minus 4. Now we will implement the Pythagoras theorem on the right triangle, triangle L and P. Repeat again, we will implement the Pythagoras theorem on the right triangle, triangle L and P. This angle equals to 90 degrees according to our construction. So I will copy the right triangle L and P in a new page and we will implement the Pythagoras theorem on this triangle, triangle L and P. Okay. We have already found out that Ln equals to capital R minus 4. This angle equals to 90 degrees according to our construction, so angle NP equals to 90 degrees. Side NP equals to X. And the hypotenuse LP, here. We already found out that the hypotenuse LP equals to 4 units. It is 2 plus 2, that is 4. 2 plus 2, that is 4. So, I copied the right triangle, triangle L and P in this new page. Now we will implement the Pythagoras theorem on this triangle, triangle L and P. So here, by PT is the abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is LP, therefore the square of the hypotenuse is LP square. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to Ln square plus Np square. Lp equals to 4. Therefore, Lp square equals to 4 squared, that is 16. That is equal to Ln square. Ln equals to capital R minus 4, therefore Ln square is capital R minus 4 square plus Np square. Np equals to X, so Np square equals to X square. So here we will open the brackets on this side of equation number 2 and we will get that (16) equals to R minus 4 squared is R squared plus 4 squared, that is 16, minus 2 times R times 4, it is minus 8R plus X squared. So here we have 16 on both sides of this equation, equation number 2, so 16 will get cancelled. And what is left from equation number 2 after we cancel 16? In this side we have 0, nothing left in this side, and it is equals to r squared minus 8r plus x squared. So here we will add 8r to this equation, equation number 2, and we get that according to equation number 2, r equals to r squared plus x squared. So here we subtract r squared from this equation, equation number 2, and we will get that according to equation number 2, 8r minus r squared equals to x squared. So we actually have two expressions for x squared. According to equation number 1, we have already found out that r squared minus 4r equals to x squared. And according to equation number 2, we already found out that 8r minus r squared equals to x squared. Now we will create equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So here, so actually x squared according to equation number 1 is r squared minus 4r, and it must be equal to x squared according to equation number 2, that is actually 8r minus r squared. Okay. So here we'll add r squared to this equation, equation number 3, and we'll get that according to equation number 3, r squared plus r squared is 2r squared, so it is 2r squared minus 4r, that is equals to 8r. So here we will add 4r to this equation, equation number 3, and we'll get that according to equation number 3, 2r squared equals to 8r plus 4r is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. So here we will divide this equation, equation number 3 by 2, and you will get that according to equation number 3, 2r squared over 2 is r squared, that is equals to 12r over 2 is 6r. So according to equation number 3, we found out that r squared equals to 6r. Here we will subtract 6r from this equation, equation number 2, and equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. So here we'll take r as a common factor from this equation, equation number 3, and we'll get that here we took r as a common factor. So what is left from r squared after we took from it r as a common factor? What is left? It is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left? It is actually minus 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we have two solutions that are possible for r, that is the radius of the quarter circle. The first solution is r equals to 0, but because of the fact that r is the radius of the quarter circle, it can never be equal to 0, it must be a positive number. So we cancel this solution, and we left with the only solution that is left, it is r minus 6, that is equal to 0. Here we will add 6 to this equation, and we get that r equals to 6 units. So the radius of this quarter circle equals to 6 units. Now we can easily find out the area of the quarter circle. And what is the value of the shaded area? The value of this shaded area the value of the shaded area it is equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The shaded area, this shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So the shaded area equals to the area of the quarter circle. The area of the quarter circle equals to the area of the circle over 2. And the area of the circle equals to pi r square when r is capital R. Pi r square, and when we will divide the area of the circle by 4, we'll get the area of the quarter circle. So in total, the area of the quarter circle will be equal to pi r square over 4 minus the area of the circle. We know that the area of any circle is pi r square and r equals to 2, so it will be pi 2 square. This is the area of the circle, pi 2 square, minus the area of the semicircle, that it will be equal to the area of the circle over 2. And the area of the circle is pi r square, so it is, and r equals to 2, so it is pi 2 square over 2. Pi 2 square over 2. So in conclusion, we found out that the shaded area equals to pi r square over 4 minus pi 2 square minus pi 2 square over 2. Capital R equals to 6, therefore r square is 6 squared, that is 36. So in total this expression equals to 36 pi over 4 minus pi 2 square. 2 square is 4, so in total this expression equals to 4i, so it is minus 4i, and this expression here 2 square is 4, 4 times 5 is 4 pi, and 4 pi over 2 is 2 pi. So in conclusion, we found out that the shaded area equals to 36 pi over 4 minus 4 pi minus 2 pi. 36 over 4 is 9, so in total this expression equals to 9 pi minus 4 pi minus 2 pi. So 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the shaded area, this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, we finished with the second question. I repeat again, the area of the shaded area, the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. So in the next step, I will summarize the lecture. We start, of course, with the first question. So in the drawing we have triangle ABC, angle ABC equals to 30 degrees, angle ACB also equals to 30 degrees, angle DAE E equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to X. Okay, so first of all we focus on triangle ABC. In triangle ABC, those two angles are equal to each other. They are both equal to 30 degrees. So in triangle ABC, we know that angle ABC equals to angle ACB. They are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that side AB equals to side AC. Why? Because in front of this angle we have side AC, in front of this angle we have side AC, and those two sides must be equal to each other, therefore AB equals to AC. Then we define angle BAD is alpha and angle EAC is beta, and we know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees plus this angle that is also equal to 30 degrees. This angle equals to alpha according to our definition. This angle equals to 60 degrees according to what is given as the question. And this angle equals to beta according to our definition. So in conclusion, in total the sum of those angles must be equal to 180 degrees according to the rule that I mentioned, that the sum of the angles in any triangle is equal to 180 degrees. So here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in this side of the equation we have 180 degrees plus alpha plus beta, and it must be equal to 180 degrees. So here we subtracted 120 degrees from this equation, and we found out that angle alpha plus beta equals to 180 degrees minus 120 degrees is 60 degrees. So in conclusion we found out that alpha plus beta equals to 60 degrees. Then we made two constructions. Here the first construction is that from point A we draw a straight line in such a way that the angle between side CA and the straight line will be equal to alpha. Again, we draw a straight line in such a way that the angle between this angle, that is the angle between side CA and the straight line, will be equal to alpha. So here this angle equals to alpha according to our construction. The second construction that we did is this construction from point C. We draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. So this angle equals to 30 degrees according to our construction. Then we extended the two straight line until they intersect with each other at point F. In this way we created triangle ACF, and then we proved that the triangle that we created ACF is congruent to triangle ABD. So why triangle ABD is congruent to triangle AFC? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. In addition, we have side AB that is equal to side AC according to what we have already found out. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that triangle ABD is congruent to triangle AFC according to angle side angle rule. I'll explain what I mean. We proved that this triangle congruent to this triangle according to angle side angle rule. Those two angles that are equal to alpha and 30 degrees and side AB are correspondingly congruent to those two angles that are also equal to alpha and 30 degrees, and side AC in triangle AFC. Therefore, those two triangles can go into each other according to angle side angle rule. Okay? And from the fact that those two triangles can go into each other, we'll conclude that side B, we will conclude two things. The first thing that we will conclude from the fact that those two triangles can go into each other is that side BD equals to side FC. Side BD equals to side FC according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding sides BD and FC must be also equal to each other. So BD equals to FC. But according to what is given as the question, BD equals to 5 units. Here BD equals to 5 units. And from this equation 5 equals to BD equals to FC, we will derive that FC also equals to 5 units. Here FC also equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Side AD equals to side AF. According to the sum rule, that corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, here AD equals to A, then from this equation A equals to AD equals to AF, we will derive that AF also equals to A. Here AF also equals to A. Okay, in the next step we joined points E and F together by straight line, and we proved that those two triangles can go into each other. We proved that the green triangles can go into the orange triangle. First of all, before that, we have already found out that alpha plus beta equals to 60 degrees, so this angle that is equal to angle EAF that is equal to alpha plus beta equals to 60 degrees. Okay, so we proved that those two triangles can go into each other, that the green triangles can go into the orange triangle. So why those two triangles can go into each other? First of all, we have side AD that is equal to side AF. Side AD equals to side AF, they are both equal to A. Okay, here. Here side AD equals to side AE, they are both equal to A, therefore they are equal to each other. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So here, angle DAE in the green triangle is equal to angle EAF in the orange triangle, they are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE equals to itself. It is a common side that belongs to both triangles, so this side equals to itself. So here, side AE equals to side AE is a common side that belongs to both triangles. So we actually proved that the green triangle ADE can go into the right triangle AEF according to side angle side rule. So I'll explain what I mean here. In the green triangle, we have those two sides and the angle between them in this triangle. The green triangle can go into those two sides and the angle between them in the orange triangle. So those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we will conclude that side DE equals to side EF. Okay, side DE equals to side EF. Side DE equals to side EF according to the rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, side DE equals to x units in its length. So we can write down that DE equals to x. And from this equation, x equals to DE equals to EF, we'll conclude that side EF also equals to x. Here side EF equals to x, so x is the line segment that we are looking for. Therefore, we will implement the law of cosines in triangle EFC, but first of all, I presented to you the law of cosines, and then we implemented the law of cosines in this triangle, triangle EFC. So what is the law of cosines? the law of cosines is true in any triangle. So if we have this triangle, triangle ABC, that could be any triangle, we know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length. Then the following equation is true, that C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. Then we implemented the law of cosines in this triangle, triangle EFC. Side EF equals to X, side FC equals to 5, and side EC equals to 4. And this angle FCE equals to 30 degrees plus 30 degrees, that is 60 degrees. This angle equals to 60 degrees, so we implemented the law of cosines in this triangle, triangle EFC. According to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Okay, so x squared equals to 4 squared is 16 plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. So in total this expression equals to minus 40 times cosine 60 degrees. But cosine 60 degrees equals to 1/2, so in total this expression equals to minus 40 times 1/2. So here we found out that x squared equals to 16 plus 25 minus 40 times 1/2. 16 plus, so x squared equals to 16 plus 25, that is 41, and minus 40 times 1/2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. So 41 minus 20 is 21. So in conclusion, we found out that x squared equals to 21. We took a root out of this equation and we found out that x, that is the length of side DE, equals to the positive square root of 21. Because x as a length can never be a negative number. So it is equal to the positive root of square root of 21. Or in terms of numbers, it is equal to 4.58 square units. This line segment DE or side DE equals to x, and x equals to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 square units. We finished with the first question. Then I presented to you the second question. In the drawing, we have a quarter circle. Inside this quarter circle, we have a circle with radius of 2 and also a semicircle with the same radius of 2 units. The semicircle is tangent to the circle at point H. That is to say, they have an external length between them at point H. And here, the circle is tangent to the quarter circle at point K, that is to say they have an internal length between them at point K. And our mission is to find out the shaded area. So because of the fact that this is a quarter circle, in any quarter circle, this point will be always the center of the quarter circle, so point O is the center of the quarter circle, and this angle must be equal to 180 degrees, to 90 degrees. This angle is a right angle, and point O is the center of the quarter circle. It is true for any quarter circle. Okay, and we have here tangent AO, it tangent to this circle is point M. Point M is the point of tendency of tangent AO with this circle. And we have the radius PM, point P is the center of the circle, and the point M is the point of the circle itself. Therefore, PM is the radius of this circle that is equal to 2 units, and the radius of this circle, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OA must be perpendicular to the radius MP. So if OA is perpendicular to MP, then this angle equals to 90 degrees and this angle equals to 90 degrees, according to rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, tangent AB is tangent to the circle is point M is the point of tendency, therefore, and we have the radius OM that is drawn to the point of tendency, therefore tangent AB will be perpendicular to the radius MO, that is to say this angle equals to 90 degrees and this angle equals to 90 degrees. And here also we have tangent, the radius PM that is drawn to the point of tendency, therefore tangent OA will be perpendicular to the radius MP, that is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Okay? Then from the center of the circle, that is to say from point P, we draw perpendicular on BO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. So actually we created here quadrilateral PNOM that has 1, 2, 3 right angles. So inside quadrilateral NPOM we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees plus the size of the 4th angle, that is actually angle NPM. In total the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we subtracted 270 degrees from this equation and we found out that the missing angle NPM equals to 360 degrees minus 270 degrees, that is 90 degrees. So we actually found out that, so this angle equals to 90 degrees, therefore inside quadrilateral NPOM we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral NPOM as a rectangle. Okay, but we also know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle NPOM are equal to each other. It means that PM equals to NO. PM equals to NO according to the rule that the opposite sides of rectangle are equal to each other. But we have already found out that PM equals to 2, so we can write here that PM equals to 2, and from this equation 2 equals to PM equals to NO, we will derive that NO also equals to 2 units. Here NO also equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, here side NP must be equal to side OM. NP equals to OM. So if we define side OM as x, here OM equals to x according to our definition, then from this equation x equals to OM equals to NP, we will derive that NP also equals to x. Here NP also equals to x. Then we focus on this point that is the touching point between the circle and the quarter circle. As I've already mentioned before, this touching point, it is defined as internal lunge between the circle and the quarter circle. That is to say, those two circular shapes are touching each other internally at point K. Point K is the point of tendency, and whenever you have an internal lunge between two circular shapes, then the straight line that joins their centers together must pass for the touching point of the two circular shapes. Point O is the center of the quarter circle. Point P is the center of the circle. So the straight line that joins their centers together will be OP. And according to the rule that I mentioned, this straight line OP must pass through point K, that is the touching point between the circle and the quarter circle. That is to say, OPK is one straight line. Okay, you can conclude from it that OPK is one straight line, or in other words, you can also say that points O, P, and K, they are all located on the straight line. Okay, so if OPK is a straight line, then OK is also a straight line. OK is a straight line. Point O is the center of the quarter circle. Point K is the point on the quarter circle itself. That is to say, OK is the radius of the quarter circle. So OK is the radius of the quarter circle, and we define the radius of the quarter circle as capital R. So OK equals to capital R according to our definition. That is the radius of the quarter circle. So here point P is the center of the circle. Point K is a point on the circle itself. That is to say, PK is the radius of the circle, that is equal to 2 units. So here PK equals to 2 units, it is the radius of the circle. OK equals to capital R, it is the radius of the quarter circle. And what is the value of OP? The value of line segment OP from the drawing is very easy to see that OP equals to OK minus PK. Again, OP equals to OK minus PK. Okay? I repeat again, OP equals to OK minus PK. So OP equals to OK minus PK. So OP equals to OK, that is 2, minus OK, that is capital R, it is the radius, here OK is the radius of the quarter circle, minus PK, and PK is the radius of the circle, that is equal to 2 units. So in conclusion, we found out that OP it is equals to OK, that is capital R, minus PK, that is 2. So OP equals to capital R minus 2. Okay, so here OP equals to capital R minus 2. And we know that PM equals to 2 and OM equals to X. So I copied the right triangle OPM in a new page, and we implemented the Pythagoras theorem on the right triangle OPM. In the right triangle OPM, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, so the square of the hypotenuse is OP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PM square plus OM square. So OP square equals to PM square plus OM square. OP equals to capital R minus 2, so OP square is capital R minus 2 square, and it is equal to PM square. PM is 2, so PM square is 2 square, that is 4, plus OM square. OM is X, so OM square is X square. So in conclusion, we found out that according to equation number 1 and according to the Pythagoras theorem, R minus 2 square equals to 4 plus X square. Here we open the brackets on this side of equation number 1, and we found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R. And in the other side of the equation number 1, we have 4 plus X square. So we have here 4 on both sides of equation number 1, so 4 will get cancelled, and we left only with R square minus 4R, that is equal to X square. So according to equation number 1, we found out that R square minus 4R equals to X square. Then we focused on this point, that is the touching point of the circle on in the semicircle. So here we have an external edge between the circle and the semicircle. And whenever you have an external edge between two circular shapes, then the straight line that connects their centers together must pass through the touching point of the two circular shapes. So in our drawing, it means here point P is the center of the circle. This point that is actually point L. Here point L is the center of the semicircle. And the straight line that connects their centers together is the straight line LP. And that straight line LP, according to the rule that I mentioned, the straight line LP that connects their center together must pass through the touching point of the two circular shapes. That is to say, the straight line LP must pass through point H, that is the touching point of the circle with the semicircle. Or in other words, line segment LHP is one straight line. Okay, line segment LHP is one straight line. Or we can also say that points L, H, and P, they are all located on one straight line. Okay, it is exactly like saying that LHP is one straight line. So if LHP is a straight line, it means that LP is also a straight line. So what is the length of the straight line LP? LP equals to LH plus HP. LP equals to LH plus HP. So LP equals to LH. L is the center of the semicircle. H is the point of the semicircle itself. That is to say, LH is the radius of the semicircle that is equal to 2 units according to what is given as the question. And here, point P is the center of the circle. Point H is the point of the circle itself. Therefore, PH is the radius of the circle that is also equals to 2 units. So in conclusion, we found out that LH equals to 2, HP also equals to 2. Therefore, LP that is equal to LH plus HP equals to 2 plus 2. So LP equals to 2 plus 2, that is 4. So we found out that the straight line LP equals to 4 units. Then we found out the value of line segment LN. What is the value of line segment LN? From the drawing it is very easy to see that LN equals to BO, that is the radius of the quarter circle, minus BL minus NO. I repeat again, the straight line LN equals to BO, that is the radius of the quarter circle, minus BL minus ON. Minus BL minus ON. So I repeat again that BO is the radius of the quarter circle, that is to say it is equal to capital R. What is the value of BL? L is the center of the semicircle. B is the point of the semicircle itself, that is to say BL is the radius of the semicircle that is equal to 2 units according to what is given as the question. So here BO equals to capital R, BL equals to 2, and NO also equals to 2. So in conclusion, we found out that the length of line segment LN is capital R minus 2 minus 2. Minus 2 minus 2 is minus 4. So in conclusion, we found out that the length of line segment LN is equal to capital R minus 4. Then I copied the right triangle LNP in a new page, and we implemented the Pythagoras theorem on the right triangle, triangle LNP. This angle equals to 90 degrees according to our construction, therefore triangle LNP is the right triangle. So this is the right triangle, triangle LNP that I copied from the original drawing. We have already found out that LN equals to capital R minus 4, NP equals to X, and the hypotenuse LP equals to 2 plus 2, that is 4. Then we implemented the Pythagoras theorem on this right triangle, triangle LNP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is LP, so the square of the hypotenuse is LP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to LN square plus NP square. LP equals to, so in conclusion, LP equals to LN square plus NP square. According to Pythagoras theorem, LP equals to 4, so LP square is 4 squared, that is 16. That is equal to Ln square. Ln equals to capital R minus 4, so Ln square will be equal to capital R minus 4 square plus NP square. NP equals to X, so NP square equals to X square. So here we open the brackets on this side of equation number 2, and we found out that here 16 equals to r minus 4 squared. R minus 4 squared equals to r squared plus 4 squared, that is 16, minus 2 times r times 4, it is minus 8r plus x squared. So we have here 16 on both sides of equation number 2, so 16 will get cancelled, and what is left after cancel 16 from equation number 2? In this side of the equation we have 0, nothing is left here. In the other side of the equation we have r squared minus 8r plus x squared. Here we added 8r to this equation, equation number 2, and we got that according to equation number 2, 0 plus 8r is 8r. That is equals to r squared plus x squared, because 8r minus 8r is 0. So in conclusion, we found out that according to equation number 2, 8r equals to r squared plus x squared. Here we subtracted r squared from this equation, equation number 2, and we found out that according to equation number 2, 8r minus r squared equals to x squared. But according to equation number 1, we have already found out that x squared is also equals to r squared minus 4r, so we have two expressions for x squared. Then we created equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So here x squared according to equation number 1 is r squared minus 4r, and according to equation number 2, x squared equals to 8r minus r squared. Those two expressions must be equal to each other. So here we added r squared to this equation, equation number 3, and we found out that r squared plus r squared is 2r squared minus 4r equals to 8r. Here we added 4r to this equation, equation number 3, and we found out that 2r squared equals to 8r plus 4r is 12r. So in conclusion, according to equation number 3, we found out that 2r squared equals to 12r. Here we divided this equation, equation number 3 by 2, and found out that 2r squared over 2 is r squared, and 12r over 2 is 6r. So according to equation number 3, we found out that r squared equals to 6r. Here we subtracted 6r from this equation, equation number 3, and we found out that according to equation number 3, r squared minus 6r equals to 0. Here we took r as a common factor from this equation, equation number 3, so what is left from r squared after we took from it r as a common factor? What is left? It is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left? It is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we have two solutions that are possible for capital R. Either capital R equals to 0, but according to our definition, capital R is the radius of this quarter circle, and it must be a positive number. It can never be equal to 0. So we cancel this solution, and we left only with the second solution that r minus 6 equals to 0. So if r minus 6 equals to 0, we added 6 to this equation, and we found out that capital R equals to 6 units. So in conclusion, we found out that here the radius of this quarter circle equals to 6 units. Now it is very easy to find out the area of the quarter circle. That is actually the radius of the circle over 4. And what is the value of the shaded area? The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So, what is the area of the quarter circle? It is equal to the area of the circle over 4. That is to say, it is equal to pi r squared over 4. R equals to capital R. That is equal to 6 units. So, it is the area of the circle over 4. This is the area of the quarter circle minus the area of the circle. We know that the radius of the circle equals to 2 units, and the area of the circle equals to pi r squared, so it is pi 2 squared. This is the area of the circle minus the area of the semicircle. That is the area of the circle over 2, and the radius of the semicircle also equals to 2, so it will be equal to pi 2 squared over 2. So here, the area of the semicircle equals to pi r squared over 4, and r equals to 6, so pi pi r square is pi 6 square, that is 36. So here, in conclusion, this expression equals to 36 pi over 4 minus pi 2 square. 2 square is 4, and 4 times pi is 4 pi, minus the area of the semicircle, that is pi 2 square over 2. 2 square is 4, so, and 4 times pi is 4 pi, and 4 pi over 2 is 2 pi. So in conclusion, we found out that the area of the shaded area equals to 36 pi minus 4 pi minus 2 pi. 36 over 4 is 9, so in conclusion this expression equals to 9 pi, that is the area of the quarter circle, minus 4 pi, that is the area of the circle, minus 2 pi, that is the area of the semicircle, will be equal to the area of the shaded area. So here 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. I repeat again, this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.